Hello. This video lecture is a part of BTech S3 mathematics paper, partial differential equations and complex variables. It's MA T201. In this paper, the first modules are partial differential equations. The course outcomes are for the first two modules. First outcome is understand the concept and solution of partial differential equation. And second outcome is analyze and solve one-dimensional wave equation and heat equation. These are the two outcomes of this topic, partial differential equation. And the topics of the first two modules are like this. Module 1 mainly deals with the partial differential equations, their formation by eliminating arbitrary constants and by eliminating arbitrary functions, then solution of partial differential equations, then solve equations solvable by direct integration, the linear equation of first order, and nonlinear equation of first order. These are the sections is module 1. Okay, and module 2, it deals with the application of partial differential equations. Mainly we have two cases, one-dimensional wave equation and one-dimensional heat equation. Okay, so these are the two modules of which deals with the partial differential equation in this paper. So the study of partial differential equations is a part of mathematics which has vast application in the field of applied science and technology. The formulation of a continuous physical system using mathematical notations and study of dynamical systems with several variables falls under the category of partial differential equations. So there are various applications of partial differential equations such as electrostatics, heat conduction, magnetism, wave motion, hydrodynamics, aerodynamics, where we use partial differential equation models. Okay. So with this introduction of the course, we'll start with the first module. So in the first module, we mainly discuss what is a partial differential equation and formulation of partial differential equation and solution of partial differential equation in some particular cases. Okay. So in this lecture, the topics we are going to discuss is what is partial differential equation and formulation of partial differential equation by method of elimination of arbitrary constants and method of elimination of arbitrary functions. Okay, so let us start with the question, what is a partial differential equation? So partial differential equation is a mathematical tool to represent a complex system with two or more independent variables. So it is a mathematical tool to represent a complex system with two or more independent variables. I think earlier we studied ordinary differential equations, where in that case, that is a tool to model physical systems having a single independent variable. Here we have a system more than one, that is two or more independent variable. And a complex system means a function of two or more independent variable with some system parameters which are either constants or arbitrary functions. Okay. So the resulting equation obtained by the elimination of these system parameters using partial differentiation is called a partial differential equation. So the partial differential equation, we have three stages. Initially, we can represent it as a tool to represent a complex system with two or more independent variable. Complex system means it is a function having two or more independent variable with some system parameters which are either arbitrary constants or arbitrary functions. Now the resulting equation, which is obtained by elimination of these system parameters using partial differentiation, is called a partial differential equation. Actually, this partial differential represents the same complex system which discussed earlier. So mathematically, a partial differential equation is an equation of this format. That is f of x, y, z, where x and y are independent variable and z is a dependent variable. Then dou z by dou x, dou z by dou y, dou square z by dou x square, etc. The derivatives equal to 0. There is an equation involving two or more independent variables and a dependent variable and its partial derivatives. That equation is referred as a partial differential equation. So the general form of a partial differential equation is this. Okay. In connection with the partial differential equation, we are using this notation for the partial derivatives. Common notations. Dou z by dou x can be represented denoted by p. Dou z by dou y is denoted by q. Dou square z by dou x square is denoted by r. Dou square z by dou x dou y is denoted by s. Dou square z by dou y square is denoted by t. These are some common notations in which we use in partial differential equation. And these are some examples of partial differential equation. The first one, a dou u by dou x plus b dou u by dou y equal to z. Another one, dou u by dou x the whole square plus dou square u by dou y square equal to 0. Dou square u by dou x square plus dou square u by dou y square equal to 0. Another one, dou square u by dou x dou y equal to cos of x plus y. So these are some examples of partial differential equation. And this is one of the application case, that's a wave equation. Actually, we will explain this in detail in our second module. Anyway, in this case, we will simply identify the dependent variable which represents the partial differential equation. So we have a string which we fix at both ends at O and this end L. Both ends are fixed. And the tension is applied on the string. Then it starts vibration. So at a certain position, time t, let p be the position of the string at a distance x. So in this case, this position, that is u of xt, represents the vibration of the string at a position x at time t. So that vibration of a string is a dependent variable, depends on the position, that is a distance from the end O and the time t. So two variables are there. So this represents a partial differential equation. Okay. So y of xt represents the vibration of a string at a distance x at time t. So it is a function, depends on more than one independent variable. So the differential equations obtained from this is dou square u by dou x square equal to 1 by c square dou square u by dou t square. This is what we referred as one-dimensional wave equation. Anyway, we will discuss this in a detailed manner in our next module. Now we have some definitions regarding some parameters of partial differential equations. That is order of partial differential equation. So as in the case of ordinary differential equation, the order of a partial differential equation is the highest order partial derivative. The order of the highest order partial derivative present in the given partial differential equation. So order of a partial differential equation is the order of the highest order partial derivative present in the given partial differential equation. So in this case, in this example, this is a partial differential equation. The highest order partial derivative present in this equation is first order. So it is a first order differential equation. In this case, the highest order partial derivative in this equation is second order. So it is a second order differential equation. Here again, second order, and this is also second order differential equation. So that is the idea of order of a differential equation. So it is the order of the highest order partial derivative present in the equation. Okay. Now another term is degree of a partial differential equation. It is the highest degree of the highest order partial derivative used in the partial differential equation. That is the degree of highest order partial derivative. So if it contains more than one terms of highest order derivative, we have to take highest degree. This is why we are writing that highest degree of highest order partial derivative used in the partial differential equation, provided the equation is written in some polynomial form. So in this equation, for the first order and the power is 1, so it's a first degree differential equation. In this case, the highest order derivative in this equation is second order and its degree is 1. So it is a first degree second order partial differential equation. Okay, first degree, second order partial differential. Here again, the degree is 1. So it is again a first degree, second order partial differential equation. This is again a first degree, second order partial differential equation. Then linear partial differential equation is a partial differential equation in which the dependent variable z and its derivative are of degree 1. So z and its derivatives are of degree 1. It is called a linear differential equation. It is also, we should note that the products of the dependent variable and the derivatives do not appear in the equation. Anyway, okay. Now we come to the main section of this topic, formation of partial differential equations. So a partial differential equations can be formed by two methods, which we are going to discuss here, by elimination of arbitrary constants or by elimination of arbitrary functions. Okay. Now, first we discuss the formation of a partial differential equation by elimination of arbitrary constants. Suppose we have a mathematical equation of this format, f of x, y, z, a, b equal to 0. This is a mathematical equation where x and y are independent variable, z is a dependent variable. A and b are two arbitrary constants. So this is a given equation. We have to form a partial differential equation from this. Okay. To form a partial differential equation, differentiate this equation, equation 1, partially with respect to x and y. Okay. So that we get two equations. So f of x, y, z, a, b equal to 0 is equation 1. Differentiate equation 1 partially with respect to x first. So f is a function of these variables. So first we have to differentiate with respect to x. F is a function of x and y. Okay. Independent variables are x and y. So dou f by dou x plus this is independent, so we can neglect this. Then dou f by, because f is explicitly a function of x, y, z, where we have to consider x and z as both are functions of x. So y, a, b are independent of x. Okay. So while differentiating by applying function of function rule, we have to consider x and z. Okay. So dou f by dou x plus dou f by dou z into dou z by dou x equal to 0. When we differentiate with respect to y, we have dou f by dou y plus dou f by dou z into dou z by dou y. Okay, so we get two equations like this. Now from these two equations and from one, that is from 1, 2, 3, we eliminate a and b. We have the equation of this format. So in the resulting equation, we have only x, y, z, p, q, because a and b are eliminated. So it should be an equation of this format, a function of x, y, z, p, q equal to 0. So that is the required partial differential equation. And it is a partial differential equation of first order. Okay, now we have some points we have to mention here regarding the order of differential equation. That is, order and degree of a partial differential equation depends the given mathematical equation and number of time differentiation occurs. Okay, that is the first point. The order and degree of a partial differential equation always depends on the given mathematical equation, because how many number of arbitrary constants it involved and how many number of arbitrary functions it involved. So it depends on that equation. Secondly, number of times differentiation occurs. Okay. Second point, suppose we have an equation f of x1, x2, x3, etc., xn, a1, a2, a3, etc., ak equal to 0. That is an equation with the n independent variables and k arbitrary constants. So in this case, k equations have to be generated by partial differentiation. K equations have to be generated. Suppose we have an equation like this, we have to generate k equations, that is as many number of arbitrary constants. As it has k arbitrary constants, we have to generate k equations by partial differentiation. That is, we have to apply partial differentiation k times. Okay, that's point 2. Now the third point, the number of independent variables equal to the number of arbitrary constants in a mathematical equation partial differential equation is always of first order. Either in a mathematical equation, if number of independent variables and number of arbitrary constants are identical, is same, then the partial differential equation is always of first order. Uh, then the fourth case, the number of independent variables is less than the number of arbitrary constants in the mathematical equation, then partial differential equation is second or higher order. Okay. Now the fifth point, if there is a single arbitrary function in the mathematical equation, the resulting PDE is of first order. But in the case of two arbitrary functions, resulting PDE can be second or higher. Generally, we choose the one with the least order. So these are some points which we have to keep in mind while forming partial differential equation. Okay. Now, I will give some problems for forming partial differential equation by method of elimination of arbitrary constants. Okay. Problem 1. Form a partial differential equation from z equal to ax square plus by square by eliminating arbitrary constants. Okay. So this is a functional relation, a mathematical relation. We have to form a differential equation from this by eliminating arbitrary constants. So consider the equation z equal to ax plus by square as 1, differentiating 1 partially with respect to x. So what happens? Dou z by dou x equal to 2ax, as y is independent of x. That term is, the derivative of that term is 0. So dou z by dou x equal to 2ax. Similarly, differentiating 1 partially with respect to y, we will get dou z by dou y equal to 2by. Okay, so we get equation 2 and 3. Now from these two equations, we can find out a and b like this. So a equal to 1 by 2x into dou z by dou x, and b equal to 1 by 2y into dou z by dou y. Okay, our aim is eliminate a and b from these three equations. So what we do is substituting these values of a and b in equation 1. Okay, so what happens? Z equal to, the equation 1 is this. So z equal to a is 1 by 2x into dou z by dou x, that into x square plus by square. So this is b into y square. So one x get cancelled. What you get is 1 by 2 dou z by dou x into x plus 1 by 2 dou z by dou y into y. Okay. We represent dou z by dou x as p and dou z by dou y as q. We get px by 2 plus qy by 2. That is 2z equal to x into p plus y into q. So that is our answer. So this is a partial differential equation which is formed by this. So what this indicates is, this is a partial differential equation where this function relation is a solution of this equation. Okay, so that's the idea of forming partial differential equation. We take another one. The second one, actually a partial differential equation represents a system of surfaces. I think we are familiar with the ordinary differential equations. A solution of an ordinary differential equation always represents a system of symmetric curves. Similarly, the solution of a partial differential equation always represents a system of symmetric surfaces. Okay, so here you have a system of surfaces. So naturally, that will represent a partial differential equation. And the problem is, find the partial differential equation which suitably represents the given system of surfaces. So the question like this: find the partial differential equation of all spheres whose centers lie on the z-axis. So the problem is, identify the mathematical relation, identify the number of arbitrary constants or arbitrary functions involved in the equation, eliminate them by applying partial differentiation. You will get the partial differential equation. Okay, so the coordinates of center of sphere may be taken as 0, 0, A, because it is a point lie on z-axis. If you take any point on z-axis, its x coordinate and y coordinate are 0, and z coordinate varies. So 0, 0, A is an arbitrary point on z-axis. So coordinate of center of spheres may be taken as 0, 0, A, as centers lie on z-axis. Okay. Then the equation of set of all spheres whose centers lie on z-axis is given by Our general formula is x minus a the whole square plus y minus b the whole square plus z minus c the whole square equal to r square. And in this case, center is 0, 0, a. So x square plus y square plus z minus a the whole square equal to b square. B represents the radius. And in this equation, a and b are arbitrary constant. Only condition given is the center of the sphere lies on the z-axis. So it can be at any point, center, along z-axis. So this arbitrary constants. And the radius of the sphere can take any value. Okay. So this may be the equation of the sphere as given in the problem, which contain two arbitrary constants, A and B. So in order to form a partial differential equation of these surfaces, we have to eliminate A and B. So differentiate this equation partially with respect to x as well as partially with respect to y. So these are the steps. This is x square 2x. This is independent of x. So here 2 into z minus a into dou z by dou x. So that is p equal to 0. So this is the equation obtained by differentiating this one partially with respect to x. Okay. Now differentiate the same one partially with respect to y. Okay. That is 2y plus 2 into z minus a into q equal to 0. So we get two equations from the equation 1. On simplifying, you will get x equal to a minus z into p and y equal to a minus z into q. Our aim is to eliminate a and b, and in this case we have two equations of this format where a minus z is common. Okay, so simply dividing these two, that a minus z get cancelled, we have an equation independent of a and b, because already b is eliminated. In this equation we have only a. So on dividing 2 and 3, 2 by 3, we will get x by y equal to p by q. On cross multiplying, we will get py equal to x cube. So this is a partial differential equation formed from this system of surfaces, set of all spheres. Okay. Now one more question in this section, problem 3. Find the partial differential equation of all spheres of given radius are having their centers in xy plane. Centers lie in xy plane and radius, given radius r, that is r is a constant. So for r is 100, whatever may be that remains same. Only changes centers can be chosen as any point in the xy plane. So here center of the sphere can be chosen as AB0, because on the xy plane only z coordinate is 0. Okay, so we can choose the coordinates of center of the sphere as AB0. Then equation representing the set of all spheres is given to be x minus a the whole square plus y minus b the whole square plus z square equal to r square. This is the equation of the sphere. Now to form the partial differential equation, differentiate equation 1 partially with respect to x and partially with respect to y. Okay, for x, this is the equation. So on differentiation, 2 into x minus y plus this is 0. Here 2 is z dou z by dou x equal to 0. On the right side, r square, derivative is 0. So 2 into x minus a plus 2 is at p equal to 0. Similarly, with respect to y, what we get is 2 into y minus b plus 2 is at dou z by dou y. That is 2 into y minus b plus 2 is at q equal to 0. Okay. Now we have these two equations. In this equation, we find out x minus a and y minus b from 2 and 3. From 2, we get x minus a as minus pz and y minus b from 3 as minus qz. Okay, so that from this equation we get the value of x minus a, and from this equation we get the value of y minus b. This is minus pz and this is minus qz. Substituting these values of x minus a and y minus b here, we can eliminate a and b. So what we get is minus pz the whole square plus minus qz the whole square plus z square equal to r square. That is p square plus p square is z square plus q square is z square plus z square equal to r square. That is z square is common, so p square plus q square plus 1, the whole into z square equal to r square. So that is the required partial differential equation, which can be deduced from this system of spheres. Okay, so these are the cases for formulating a partial differential equation from a mathematical relation by eliminating arbitrary constants. Okay, with this, this lecture is over.